Our focus for this next series of videos is going to be on convergence testing for infinite series. So if we take a sequence and run the sequence out for an infinite number of terms, we add all those terms together, will there be a sum that exists and can be calculated? So if we're going to define a sequence as u sub k, where u is any term and k is the number of terms that we have, we can create a divergence test by looking at the limit of the value of this series as k goes to infinity. So here's the divergence test. Basically what it says is if we take the limit as k goes to infinity of the sequence, and the limit turns out to be not equal to 0, or it doesn't exist, then we can guarantee that the series, that is when we add all the numbers together, we're going to have a divergent series. That is, there will not be a sum beyond infinity that we could actually, or beneath infinity that we could actually use, calculate. The divergence test is really straightforward. We simply see what happens to the value of the sequence as k goes to infinity, and if it's anything but 0, we know divergence. So this test is a useful test because if you are asked to show if something converges, and you can see from the limit test here that we don't get a 0 limit, then you can stop testing for convergence because you know you have divergence and you can, just quit. So it's a quick test and it's easy to do, but just to explain it a little bit more, we're going to look at the series where the sum goes from 1 to infinity of k squared minus 3 over to that quadratic denominator, and we want to show that this is divergent. First of all, just looking at the sequence of numbers, we can see all of these green points representing increasing values. But these values start to converge upon the number 1/2, y equals 1/2. So basically, as u sub k approaches infinity, as k approaches infinity, it appears that u sub k is going to get closer and closer to 1/2. If we have infinite terms in this series, then there's going to be infinity numbers, all of which are bigger than 1/2. So, in other words, if we look at the area under this curve and we consider the fact that this rectangle is going to be infinitely expanding to the right, there's no way that this is going to converge on a singular number. So the series, that is the sum of all these numbers up to infinity, diverges to infinity. Now to prove that, we just have to take the limit. So we just take the limit of the actual terms of each of the series, that is the limit of the sequence. And this technique is really handy in working with any sort of polynomial rational functions. We just basically divide top and bottom by the highest power of k, and in so doing, we will have two constants, and the rest will be decreasing positive or decreasing functions. In other words, as you let k go to infinity, this 3 over k squared will approach 0, and so will all of these where the denominator is increasing to without bound. So all of these 0 out, and we're left with the 1 over 2, which is 1/2, which is demonstrated by the graph and the table. But now we have an elegant limit proof to establish this. And since the limit as k approaches infinity of u sub k is not equal to 0, we can say without question the series, well, this says converges, what I meant to say was diverges. So we'll just erase that and write it correctly. Sorry about that. Alright, moving on. If we try to do the divergence test and we find the limit approaches 0, we need to understand just because the limit of the sequence approaches 0, that doesn't mean that the series is convergent. It just means that we are inconclusive on the divergence test. So we have to have other tests for convergence once we establish that the divergence test has failed to give us any sort of divergence. So here's an example. Is this particular series convergent? Now I'm mentioning something here about an integral test. This is something that we'll see a little bit later. But if I wanted to try the integral test, I can't integrate this particular function. So the integral test isn't going to help me at all. Just briefly to explain the integral test, if we look at the sequence and we treat the sequence as a continuous function and then integrate that function to infinity, and we can get a limit for that integral, then we know if the function converges, it has a finite sum, then so too will the series that's related to that function. So that's what the integral test is about, but it's only useful if we can integrate the function that we're trying to study. So what we're going to do instead is compare this series to a similar series that we know is always going to be bigger. So anyway, what's happening over here in the graph is clearly the sequence does have a zero limit, but does the series actually converge? And that's what we're trying to establish. So let's compare the denominator, 3 to the n plus n, to a simpler denominator that would be 3 to the n. We know that 3 to the n is always going to be smaller than 3 to the n plus n because n is always going to be positive, and therefore we can say that the reciprocals are also related. So if the denominator is bigger than this denominator, then 1 over that number is going to be less than 1 over that number. So that's our logical argument. So now we know that this sequence, the red one, 1 over 3 to the n, is always going to be larger than our sequence. So if we can show that this sequence converges, then we know that this if this series converges, then we know that this series is going to converge as well. That's what I was about to write here. If you examine the series, 1 over 3 to the n, you should recognize it as a geometric series where r represents the common ratio. We're just multiplying by a third each step of the way, and the first term in the series is 1. And therefore, we can find the sum of an infinite series using 1 over u sub 0 over 1 minus r will give you the sum of the geometric series. We've seen that before. In this case, it's 3/2. So if I look at the partial sums for my series that I'm trying to compare, these partial sums are always going to be less than the partial sums of the geometric series, which is always going to be less than the infinite sum of the geometric series, which is 3/2. So I don't know what the sum of my infinite series is, but I know for sure it's always going to be smaller than 3/2. Therefore, we can say that the series converges. Alright, so we look at another example of the comparison test, and here what we see is exponential growth functions, if you will, that are being added together in the numerator and the denominator. We need to use the comparison test to show that this indeed converges. And I had to think about this one for a while. Eventually, I remember that if we choose the largest term of the numerator and compare that against the smallest term of the denominator, we will guarantee larger numbers in our ratio. That is to say, the ratio comparing the sums of these exponentials is going to be smaller than the ratio comparing my geometric series. And just to confirm, since we will have the technology on paper 3, I would graph 3/4 to the k, which is this blue curve, and I would graph the other thing that I'm trying to prove, and just to demonstrate and make sure that indeed we're always going to have larger values for 3/4 to the k. We can stretch it out for a while and make sure, even though we have our common sense and reason, we should make sure our reason is sound. So for all positive k's bigger than 1, we can guarantee this to be true, and since this, once again, is a geometric series, we can find the sum to infinity is 3, and since that exists, and it's bigger than all the values of my series, I know my series converges too. So that's the comparison test. That'll conclude this video. In the next segment, we will explore the comparison test one more time and see where it has limitations. And we'll get to that one in just a little while. This is going to be the start of the next video. So, all right.